All right. Hello, everyone. Thanks for coming. My name's Ofer, and I'll talk today about Bayesian networks with R and Hadoop. So let's get started. So a little bit about myself. I work at Hortonworks. I run our data science team. What that means is we're part of the services at Hortonworks, and we help our customer with everything that they have to do related to data science, of course, focusing on Hadoop. Previously, I worked at places like Nora1, Yahoo, Quiver, and if you're interested, my son plays chess, so I have a little personal blog where I write about my experiences as a chess dad and my personal life. So this talk today is about Bayesian networks. So I'm going to start by giving a very, very quick overview of what that is, what are Bayesian networks, why I think they're cool, and I think that they're not very popular. Some people learn them in college or different other places in the past, but I don't see a lot of usage for them. So I kind of explored that in the last couple of months, and I want to maybe get your interest up to explore that as well. That may be one of my goals here. And then what I'm going to show is using a particular package that can do a lot of stuff around Bayesian networks, not everything, called BNLearn. And I'll show you how to use that package, a couple of techniques, and then at the end, we'll see how we can leverage Hadoop as a kind of a grid computing, a really large-scale compute resource. If you have a Hadoop cluster, you can actually parallelize some of the computation to make it more feasible for really large networks. So let's get started with the introduction. So here's the pieces of a Bayesian networks, and I'm giving an example here of this very popular in the literature of Bayesian networks, an example called Asia. As you can see, I'll try to use my pointer here. These are nodes. They are representing random variables. In this case, I chose a simplified example where they're binary, so they got yes or no. So have you been to Asia? Are you smoking? Do you have these kind of diseases, tuberculosis, lung cancer, bronchitis? And so these are called the variables and the nodes of the graph. And then there's arrows. So you point these arrows, and the arrows are essentially saying that they reflect these either causal relationships, although I'll talk about it later. It's not exactly necessarily causal, but it's a conditional dependence between the graphs. So, for example, if you're smoking, so lung cancer and bronchitis depend on whether you're smoking or not. So there's some conditional probabilistic dependence between those things. So you put in the nodes, you put in the edges, and then the third thing you have to do is this thing called the CPT, which is the conditional probability table. And it's a table for binary variables. It could be something else for Gaussian Bayesian networks. But in this example, you can see that this node, every node has a CPT. And this node, you can see all the possibilities here. We got tuberculosis or cancer. Could be true or false. Bronchitis could be true or false. And then based on that, you have shortness of breath. It could be true or false. And by the way, shortness of breath in the medical community is SOB. Sorry about that. That's kind of how it is. So when your doctor says something like that to you, don't get insulted. It just means that, anyway. But that's essentially, those are the components of a Bayesian network. Again, it's a simplified version. So you got nodes. The edges have to be a DAG, a directed acyclic graph. And you got nodes, you got edges, and you got conditional probability tables. Once you have that, that's your model. That's your Bayesian network. Now you can start working with it. And we'll talk later on of how to build it and then how to infer with it, OK? So I want to talk a little bit about why I think Bayesian networks are cool, what's interesting about them, what's different about them a little bit. So there's a couple of things. First, they're a very intuitive modeling tool. So you can look at a lot of different real-world problems, and you can easily understand, yeah, that's a good node for me, that's a good node for me, and the arrows are pretty natural. If, for example, if you've visited Asia and you got the Asian flu or whatever you might have, some of these arrows are very natural. If you're smoking, yes, you're going to have lung cancer. So there's an ability to include expert knowledge pretty easily to kind of build your model. So it's a very intuitive modeling tool for a real-world problem. It's also, of course, easy to combine expert know-how in it. And the other thing is you can start with a small network, and as you learn more, you can add nodes or add more arrows as you kind of learn more about the problem. and kind of adapt the network to the model to where you want it to be. The other thing that I really like is that it has a natural way to deal with missing values. So in practical data science in the world, most traditional, let's call it supervised learning models, even unsupervised, they require you to have a set of features, and then you have a target function. And you really have to have all the features to learn. So it's required and to infer, too. You have to have the complete data set. If you don't, there are techniques by which you can impute missing values and things like that. But generally, you require all the data, all the features. And with Bayesian networks, especially with inference, there's a very natural way to deal with missing values that's quite compelling in a lot of cases. And then the other thing is you don't have one target variable. Like in supervised learning, you're predicting, let's say somebody was going to churn or not in the next 30 days. You decide what your target function is, and you build a model just based on that. And your model can predict that target variable. In Bayesian networks, you can actually ask a question or do inference on any node in the network. So you can do it on all your model. You don't have to decide up front which one you're going to do. And we're going to see that later on. So a little bit of use cases. So Bayesian networks have been around for a long time. They've been studied in universities and academia. They've been used in practice. Some of the use cases you can see here, healthcare is very common, either in genomics and medical diagnosis. There's been applications in security. There have been applications in finance for fraud detection. A lot of different applications. In fact, actually, one of the things that I found was a couple companies, I think Microsoft, maybe, I'm not sure if it's Microsoft, a couple others have used it for like, this is probably 10 or 20 years ago, to do diagnostic troubleshooting for customer support. You call someone, you say, I got these things when my computer doesn't work or Windows or whatever, and they tell you kind of what's the most likely thing that's going on. So it's been used a lot. And if you're interested more, there's a book that's has a large set of practical application examples there you can look at. So let me move over to a little bit more details of how we do it in practice. So there's a lot of different packages around, some commercial, some open source. I chose to work with this package called BN Learn. It's written by, it's an R package. It's written by this guy, Marcus Guttari from University College of London, who's an expert in this field. And the reason I chose that one is because it's really nice, it's well developed, it keeps being updated. And what it allows you to do is a lot of the different steps of building a model. And so building a model, you do structure learning. So it can automatically, so if you know the expert knowledge and the arrows of what they need to be, you can use that. But it also allows you to learn the arrows automatically from data. So we'll talk about structural learning. And this package implements a bunch of algorithms like hill climbing, taboo search, growth shrink, a couple other names that you'll see in the literature if you research this more. It also provides automated learning of the CPT tables, the parameters of the network after you have the structure. And it does approximate inference. So in inference, in Bayesian network, we have exact inference and approximate inference. I'll talk about that a little bit later. It only implements approximate, two techniques called likelihood sampling and, sorry, that's actually supposed to be logic sampling and likelihood weighting. And there's a couple others, approximate techniques, and there's exact. But this is nice, and I can show with this package kind of all the steps of using Bayesian networks. One other thing that's interesting, it also supports, R has a parallel processing framework called Snow. It's a package in R, and it supports, some of the algorithms support Snow, and you can kind of integrate it and get better performance with it. So, and if you want to read more about Bayesian networks in general, R has a page, a web view that can give you all the things that has Bayesian in them. But they're not all Bayesian networks, but you'll find some other packages for Bayesian networks in that page as well. All right. So let's go through the example again. So constructing the graph, okay, so we figured out the nodes, and we're gonna kind of want to understand what the edges are, what the arrows are, right? So there's two ways, as I said earlier. You can get an expert. So let's say it's a medical thing here. So okay, we'll get a doctor, and they're going to tell us, yeah, if that arrow needs to be there, that arrow needs to be there. You can also learn it from data. And learning it from data, this is how you learn it manually, okay, with BN Learn. So this is our code. I hope it's clear enough for those of you who don't know R. But so what I'm doing is I'm including the BNLearn library, defining the variable names I have. And essentially, I'm building an empty graph and then just populating it with the arrows. I'm saying the arcs of this model are between Asia and tuberculosis, smoking and lung cancer. I kind of populate the arrows. And there I got the network. And then if I plot it, I get this view, right? As opposed to doing it automatically. So here, I just call this function that's a little bit in bold here. HC hill climb is one of the techniques to build the graph automatically. And as you can see, by the way, I got a little bit of a different network. And that's something I want to point out. So these techniques are generally learning the structure of a network like this is an NP-complete problem. Okay? And this is even a simple problem. So imagine if so. NP-complete means it's really hard to know what the right one is. And learning it from data is not ideal. It doesn't work all the time. Now, it may not learn the right edges. Okay? If you know what they are, that's good, and at least you can test. Sometimes you don't know what the right edges are. And it may learn the arrows in the wrong direction, too. So a lot of times, a couple of these algorithms can learn five different networks that look to the algorithm the same way, but they have different directions. So what I found useful is to combine manual and automated learning. So and BNLearn has this concept of whitelist and blacklist. So if you know in our previous network, you have some medical doctor that tells you these are 3 arrows that you got to have. You kind of put them in, and you say these are arrows in the other direction you never are going to have. You kind of put those as blacklist, and then you let the automated algorithm work its magic from there. So this hybrid approach usually works pretty well. I wanted to also mention there is another technique also implemented in BNLearn, which I'm not going to talk about a lot, called Bootstrap Learning. And what happens with that is you can actually learn, let's say, 100 different networks using HC or Taboo or different algorithm, or even but every time you learn it on a different bootstrap of the data. So if you have, let's say, oops, I almost took this away. If you have 100,000 rows in your learning, can you hear me? Yeah. If you get 100,000 rows, you choose a bootstrap, 100 different random samples of that, and you learn differently with each of these bootstraps. And then what you do is you average the networks at the end, and you take the directions and the arrows that are more strongest, essentially, by averaging. And that seems to work pretty well in some cases, too. And it's interesting because, so BNLearn doesn't support it on Hadoop, so I'm not going to show that, but I just wanted to mention that. I think that's a parallelizable, easy parallelizable use case that you can do. So we learned the structure. So we had the nodes, we learned the structure. Now we want to learn the CPT. Okay, remember we talked about that. So how do we learn the CPT? Again, with BNLearn, you have this really simple function called BNFit. You give it the structure. You give it your data set, Asia in this case, and that's it. It learns it. Usually that's actually relatively quick, depending on the size of the data and how many nodes you have. And there's a couple other versions. There's a couple of methods. There's a maximum likelihood, and there's a more of a Bayesian approach. But usually what you get is, and I'm showing the printout of one node here. So it learns for all the nodes, but for the shortness of breath node, you can see that I got a 2 by 2 by 2 matrix, which is kind of all the possible options here. So if you don't have tuberculosis or lung cancer, then if you have shortness of breath and you have bronchitis, then your probability is going to be 0.7862. So it kind of gives you probabilities for each type of, in this case, 3 variable combination. So now let's go to inference. So again, I put the nodes, I built the arrows, I have the CPTs. Now I want to use this. Now I got my model is ready. I want to use it for inference. And that's where I talked earlier about the missing data, and that's interesting. So here, and I'll go to that. How you do that is you say, let's say I have a patient or a person I want to kind of model with this and to see if they have lung cancer. And so what I'll do is I know they visited Asia, so I have that variable as a yes. I know they have been diagnosed with bronchitis, so I know that's a yes too. And I know they currently have shortness of breath, because I see that I diagnosed them as a doctor. By the way, it could be a no too. But I have evidence for these 3 nodes, so I put those in the network, and I tell the network that I have the data for these 3 variables. I don't have the data for any of the other variables. Now, for lung cancer is what, in this case, maybe I'm trying to predict. But the other ones, it's missing. I don't have that data. It's still OK. You say, this is the evidence we have. And the network can answer the question of, what's the likelihood that they have a lung cancer? Now, by the way, you can ask this of any node. If you ask what's the likelihood they have visited to Asia, that's going to be 100%, because you just told that's evidence. But if you ask them what's the evidence of having tuberculosis or cancer, it'll be some probability. And usually what you do is you say, if you want to do a classifier, for example, you can say if the probability is above a certain number, then you can solve a classification problem that way. And this is really important. I mentioned this earlier. This is one of the things I like about Bayesian networks is in inference, specifically, you don't have to have all the data. In a lot of very practical applications, we don't have all the data. So you can imagine, we talked about medical here. You can imagine a lab that's used to diagnose someone, but if they haven't done the lab, you don't have the data, Or, a lot of times in just practical applications, like I think in genomics, for example, they use, genome expressions is a lot of very popular in features. And sometimes you measure those with the machines that, that do the sequencing. And sometimes the output of that is kind of noisy, and you don't have the data. So what do you do? So this is very useful in this case. So let me show you how you do inference. And I'm branching here into another package called grain, which is also a package in R that does exactly inference. Because as I mentioned, BNLearn doesn't do that. But they cooperate really well. So the Marco Scutari, who wrote the BNLearn, kind of had interfaces to a lot of other packages. So it's collaborative. So you can learn with BNLearn and use grain for exact inference. So what we see here is you take the fitted model that we fitted with the CPTs previously. You convert it to a grain with as grain. You convert it to a grain structure. And then there's this thing called compilation. So the exact inference algorithm that's very popular is called the junction tree propagation algorithm. And I'll tell you in a minute why it's not very practical with large data. But I just want to show how it works. So you compile the network. It converts it into a junction tree. Then you set your finding. You say, hey, I have Asia is yes. Shortness of breath is yes. Bronchitis is yes. And then you call this function called query grain. You say, I want to query using grain with my result of the junction of the evidence in the tree. And the node I'm interested here is just one node, is lung cancer, and it'll give you the answer. In this case, it's probably a no. All right? Now, let's look at approximate, and then I'll get to when to use which. There's 2 algorithms supported in BNLearn. One is called logic sampling, and they're both with this thing called CP_query. So this function CP_query, you give it the event. In this case, I'm trying to, in this case, I'm not looking at lung cancer, but shortness of breath. So I'm trying to figure out whether shortness of breath is yes. And I'm giving it 2 pieces of evidence in this case that visited Asia and have bronchitis in the second line. And the method is logic sampling, and it gives me an answer. And in the bottom part of the screen, you see it's the same thing. The calling sequence is a little different. You have to declare this variable called evidence, and you give it the values yes and yes, and you call it a little bit differently with the LW method, which is likelihood weighting, and then you get a very similar, and because it's approximate and the methods are a little bit different, you get 0.n and 0.79. It's close enough, but that's reasonable. And this is how you do inference. So I kind of went through what is it and how to use BNLearn. And that's all kind of because I wanted to talk to you about large-scale networks. And I want to show you how to use that with Hadoop to do inference as a parallel computation. So what do I mean by large? Well, if you look at the Bayesian network literature, that a lot of it is from the 90s or 2000s or even earlier than that, the networks are really small, like we saw here, like 5 nodes or 10 nodes. When I think of large, tens of nodes is medium. Of course, we went a long way. We have much faster computers, much more memory today. But I think of hundreds of nodes is starting to becoming large, and thousands of nodes is really large. That's where you start to really have trouble. And of course, it depends on the structure of your network and how many arrows you have and how many nodes. And also, it depends, of course, on the number of instances. When you do learning from data, if you have, So I think of, in my mind, sort of hundreds of thousands to 1 million rows is starting to be large, all right? Now, you don't plot these things, because you're going to get this, right? It's not really useful. It's hard to visualize these things, right? It's hard to debug them. It's much easier when you got 5 nodes and you can see. And the other thing that's problematic is you can construct a graph. You can tell a doctor, hey, I got 1,000 nodes. Go work for a year, and maybe you won't make a mistake. It's really hard. So that's where automated learning becomes a lot more useful and a lot more interesting when we go to larger scale networks. So I don't have enough time to go through learning at scale, but what I want to do is show you inference in scale. Learning in scale is not fully solved, in my opinion. There's some solutions to that, and I'm happy to talk to you afterwards if you're interested. But generally, the technique that I use mostly is, and the steps you go through is the same steps. You define the nodes. It's really important to seed whatever knowledge you can have, seed the network with that blacklist and whitelist, because as the learning problem becomes bigger, it's much harder for the algorithm to even be correct. So the more hints you give it through blacklisting and whitelisting, it's better. And then you augment the manual with the automated learning. But I want to talk about inference. And before I go to show you the code for that in Hadoop, I wanted to talk to you a little bit about the exact versus the approximate. So exact inference, like GRAIN type with the junction tree, is really fast. It takes an instant. It's very fast. And so the question is, why don't you use that? And the answer is, it's got scalability problems. And what I mean by that, when you really get to larger networks, GRAIN is sort of exponentially amount of memory to actually do its junction tree calculation. It depends roughly on what's called the graph width, which is the size of the largest click in the graph. But once you get above a certain number, I mean, it becomes a problem, and you can't build a graph correctly, and it just takes a long time and a lot of memory. So approximate algorithms are very popular because they can handle larger graphs, but the inference with approximate takes longer. And this is why I was thinking, hey, if we can parallelize this on Hadoop, think of Hadoop not as for large storage in this case, but a platform for just parallel processing. And so if I have, let's say, 1 million instances to classify, and each of them takes, let's say, 1 second or 2 seconds, that's a lot of time. But what if I split it into 100 nodes or 200 nodes, and I get each node to, on its own, classify 1,000 of those? So it's a completely embarrassingly parallel problem. And so what I want to show you is how I do that. I'm going to use this package called R Hadoop, or RMR, which is a package that's supported by Revolution Analytics. It's open source. For those of you who are not familiar, it's a pretty cool package. And the guy who wrote it, Antonio, I think is not able to be here today, but is giving it great support. And I'm going to show you. It's got a lot of packages, including RHDFS, RHBase, PyRMR. But I'm going to use RMR, which is one of the main components there. And I'm going to show you how to use it for the application I'm playing. So this is my game plan. Okay, before I go into the code, I want to explain what we're doing here. So one of the problems is that you want to do let's say 100 mappers. It's completely parallelizable. So you want to do like 100 mappers and split your data set of 1 million things into these 100 mappers. The problem is Hadoop is actually, it's quite challenging to do that because you don't control the number of mappers directly. It's kind of computed from the file size, and the file size in this case could be pretty low. So I kind of did a little trick. what I did is I said, I'm going to have a few mappers, whatever Hadoop decides to do for me, but then I'm going to randomly shuffle them to multiple reducers. So the mapper is a no-op, essentially. It just takes the thing, reads it, and shuffles it back to the exit. And most of the CP query, the actual inference, I'm going to do in the reducers. And controlling number of reducers is easy. I'll show you how to do it. It's a parameter to the job. So let's see. For this demo, and by the way, all of this is in GitHub, and I'll have the link at the end. So I build it so that it's a relatively small data set, so you can try it on a virtual machine, sandbox, and you can repeat all of that. And there's more details very detailed on the GitHub. But what I used is this adult data set. It's a very old machine learning data set that was created by Roni Kochavi and Barry Becker back in '96. And I chose this randomly just because I thought it was a nice data set, and it's got some of these data sets have just 1,000 instances. This had like 50,000. It's not huge, but it's big enough to be interesting, and it's small enough that you can do it as a demo on your virtual machine in your laptop. What this is it's based on census data, and it's got 14 features, and we're trying to predict the income if it's above 50K or below 50K. It's a very old KDD data set that's been out there. This is some of the data, what it looks like. You got all kinds of features. So just to show you, I kind of did a little bit of automated learning on this, and this is the features. This is what it came up with. I don't want to spend too much time on this. These are some of the features. I translated them all to some binary features or multiple category features. And this is how we use RMR. So with RMR, there's this function called, oops, let me go back. There's this function called MapReduce, okay, in R. It's a function in R. You give it an input file. In this case, it's the file that I copied over to the Hadoop cluster. It has all the features. You give it an output file, and you give it a mapper and a reducer. So what RMR does is you can write your mapper and reducer in R, not in Java, and that's why I'm using this. So it does a streaming job on Hadoop, and instead of streaming in Python or instead of not streaming in Java, the mapper and reducer can be written in R. So I want to also note that here there's these RMR options, and as I said earlier, I can control the number of reducers. There's a parameter called mapreduce.job.reduces. And if you set that to, in this case, I set it to 4 because I want to run it on my own little laptop. But if you have a big cluster, of course, you can set it to 100 or 200 or whatever you want, or 1,000. And that controls the number of reducers. I also set the memory I want from each of these reducers to have so that I have enough memory. And then I run this job. Now let's look at map func and reduce func, and I'll show you what you do there. As I said, the mapper is just a no-op. So the only interesting piece here is you get the values and the keys. I kind of go through each of the values. RMR sometimes batches those in a data frame, so you don't get them one by one. You get them in one chunk. So I have to kind of loop through them in case that happens. And then I essentially create a new key. If you see here, RUnif is a random number generator between 0 and the number of reducers. And I shuffle it to one of the reducers that I generated to actually do the inference. And then this is where all the work gets done. This is my reducer. And I'll go through this quickly. One of the things that's interesting is this increment counter. So when you do this is a compute-heavy job. Okay, we get one line, and we maybe spend 1 or 2 seconds on it. And then we get 1,000 lines, we can spend a couple of minutes on it to crunch through it. You want to let Hadoop know that you're not dead, because Hadoop sometimes, when there's too much, a job is taking too long, it'll try to kill it because it thinks it's stuck. So incrementing this counter helps with that. It kind of is a trick to let Hadoop know that you're not dead. It's also nice because you can then look at the logs and see where you're at, how many of these rows you've already processed. So I do that. Then I sort of split this into the features. It's just comma separated. I have this function I didn't talk about called data prep. It's on GitHub. You can take a look at it. But this generally massages the features a little bit to make them kind of cleaning up a little bit. Nothing major, just a list of some of the things are a little bit messy, and I kind of cleaned them up a little bit. But the important piece is after that you get this variable PV, which has the variable of your features. And what you do is I create the evidence. In this case, I don't have missing data in this data set, which is one of the downsides of this. I don't have missing data. So I'm just taking all the other variables other than income, which is what I'm trying to predict. So evidence will be all the other variables, and I just give it to CP query. I get the result, which is the probability, and then I'm creating an output, in this case, which is all the row with all the features, and add to that the probability at the end. Okay? And then I output that from my reducers, and then Hadoop, of course, aggregates all these outputs from all the reducers, puts it into the output file, and I'm done. This is what it looked like, right? So the output file looks similar to the input file we saw earlier. You just have this 0.37 or 0.14 or whatever. Of course, I mean, you can do the output whatever you want. I just chose to show the whole thing plus the output. You can just output the probability if you want. And that's how it works. And as I said, there is a GitHub repository that I put together, and I encourage you to try it out. It's really cool. You can download the Hortonworks sandbox. I tried it on that. You can install everything, play with it, maybe build your own network with a different data set and see how that works. If you're interested, Bayesian Networks is a really deep, complex topic to understand theoretically. I really recommend there's a probabilistic graphical models class on Coursera that Daphne Koller did. And it requires a lot of time and commitment, but if you're up to it, I recommend it. It's really good. There's also a nice book from David Barber on University College of London that's free. You can download and you can read that. If you're interested in Be and Learn, there's a website, and there's also stuff on the CRAN for R. And there's a lot of other papers and books and whatever. There's a lot of stuff about this. And that's it. Thank you very much, and I'll take any questions. Yes?
Example, like the Unit package you showed is more like a black box sort of thing, right? So in a practical setting, if you get an output number, you just get a number, right, of probability or something. How do you verify that other than using validation data set? Especially when a customer says, why was this X 94%?
So the question was, how do you validate? You get an inference number, like a probability, and how do you know that it's correct? So, like any model, I mean, you can ask the same question on any modeling technique. But I think in this case, first you can look at the CPTs. And if it's not complicated enough, you can kind of look at that and see if it makes sense. When you get to a larger network, it's hard. I mean, it's hard to do that. Also, the other thing to be careful about is sometimes very small differences in the probabilities in a Bayesian network can actually have a large impact. So it's somewhat non-intuitive. So I don't have a really good answer other than what you suggested, which is validation. So you hold something out and you try to see how it works, and you measure. If you do a classification, you can measure, your confusion matrix, or if you you can measure error rates, things like that. The traditional techniques.
You can get away in academic settings, but in practical setting, there's a customer, right? They say, why is X classified as this, and they need a real answer. You cannot just say my B impact, no impact, it's emitted 95%. That's right.
Yeah, it's hard to track down the paths of the network. I got to think about this. Maybe there's a little trick, but I can't think of something right off the top of my head.
And one more question, especially for this medical thing, when you say, is there a way to tune the false positive or the false negative rate or something of these outputs?
Say that again. What's the question?
Is there a way to tune the false, is there a way to tell the model that I'm more sensitive to false positives or something?
Yeah, so the question was, is there a way to tune a model, tell it to, like, for example, false positive, false negative trade-offs? So there is actually, so first of all, depending on what method you use to learn the probabilities, but for example, when you learn the CPTs, you can give it prior, Bayesian priors probabilities to impact the learning a little bit. So if you know that something is, so you can play with those things. In Bayesian Learning, I think it's called an ISS parameter. You can look at that. And there's a couple places where you can play with the parameters of the learning algorithm. and trade it off. It's not directly that you know, oh, I raise it and I get the, you have to play with it, but there are tuning levers there, yes. Yes?
What's the advantage of running R on Hadoop for the machine learning library versus the Python?
I work with Python. The question was, what's the advantage of running R on Hadoop versus Python? I work with both. I think they're both wonderful. In this case, I chose to show R because the BNLearn package is very thorough and helpful and shows all the things. There is a package that I'm not that familiar with called PyMC that does some Bayesian Networks learning. There's probably a few others. And I don't have on top of my head like a comparison of which one is better. But I think they're both great. Yeah. Yes?
Does the algorithm work with continuous data too? Or?
Good question. So does Bayesian network work with continuous? Yes. There is what's called a Gaussian Bayesian networks. These are discrete because they have either binary values or a few categories in each variable. There's also a Gaussian version. I think it's a little bit complex to mix it together, so you have to choose which one you're using. But yes, there is definitely a version for that. Yes. Yes, at the end.
I think I understood the part where the reuse function had a fitted model and you were using MapReduce for the inference and function nodes. I didn't get the part where that model was actually built. Was that built using MapReduce or?
The model for the example with Hadoop, I didn't show that because I didn't have enough time for this, but I built the model separately in R outside, and then I just used this. Once it's built, and then I use that to do inference and scale.
But, so the training was done on like one machine?
Yes, one machine. Actually, in this case, it's a relatively small network in terms of number of nodes, so I just trained it on my laptop.
Do any of these packages support doing that kind of training using MapReduce?
So no, and that's what I said earlier. It's possible to do it, but right off the box right now, they don't have it. BNLearn supports the Snow package for parallel computation just within R. So with Snow, you can set up, if you have a multi-core, you can start multiple processes, and sometimes you can set up other R machines and start a cluster. But it's not Hadoop, so it requires you to just set up another cluster on the side, which is kind of inconvenient. But I think that actually, I'm hoping at some point we'll get somebody to work on that, because I think it's actually really easy to port some of the algorithms in BNLearn. You give it the same interface as Snow, and it just does this across a bunch of Hadoop clusters. There's no difference. It's parallelism. So I hope that'll get done soon, and I'll help do that. Yes? Anything else? OK. Thanks very much, guys.